Hello, so we will start the chapter 7 review. Chapter 7 title is Reactions in Aqueous Solution. And you can see here the home page of Canvas or Canvas course. And here I'm showing the chapter 7 module. And I want to emphasize that there are two documents here that I strongly recommend that you use. For while you do this review, or whenever you are learning on chapter 7. So the solubility rules and polyatomic ion document, you know it already. It's this document that has the list of polyatomic ions. Oh, let me show it first. So that's the document that has the list of common polyatomic ions. And you know this table already. And if you move to the bottom of that page, there is the solubility rules, which is what you need when you need to decide if a compound is soluble or not in water. So this applies to solubility in water. So we will use that. And the other document is a PowerPoint slide with just a few slides that summarizes what you will go through in this chapter 7. And there are the different types of chemical reactions, right? We will study precipitation reactions, acid-base reactions, gas evolution reactions, and oxidation reduction reactions. And combustion reactions are a subtype of oxidation reduction reactions. And here there are the patterns to look for to decide what type of reaction you have. For precipitation reactions, you want two soluble ionic compound making one insoluble compound, right? So one of the products should be insoluble, starting from two soluble solutions. Acid-base reactions are recognizable because you have an acid plus a base reacting to make a salt, which is an ionic compound. Soluble or not, it can be both. And then water. Gas evolution reactions are when you are mixing two soluble compounds, and then one of the products is a gas. And combustion reactions, which are, redox reactions, oxidation reduction reactions, it's when you have something that is burned with oxygen from the air, and then the product will differ. But for example, when you're burning something that contains carbon and hydrogen, you will produce carbon dioxide and water. So I want you to explore all of that. And this first slide here is for the gas evolution reactions in particular. But so if we look at this here, and now we want to answer the first question of our chapter 7 review. So I want you to really notice that the chapter is on reactions in aqueous solution, right? So you always have reactants that are in aqueous solution, mostly in this chapter. It is important to recognize that when you're trying to decide if you have an acid-base reaction, precipitation reaction, or a gas evolution reaction. So question 1, what are the 4 driving forces that will cause a chemical reaction to take place? So there are typically 4 driving forces that will make a reaction happen. They will proceed, if you will. They will not just wait. These reactions will happen when you have these forces. And they are. And so for each driving force, you will have, it will refer to one of these type of reaction. And so the precipitation reaction here, the driving force is the formation of a solid. For the acid-base reaction, it's the formation of water. For the gas evolution reaction, it's the formation of a gas. And so every time here, you're starting with 2 aqueous solutions. And the driving force for oxidation reduction reaction is the transfer of electrons. So if we summarize this, here we have the formation of a solid for the precipitation reaction. That's the driving force. Formation of water for the acid-base reactions. So we know that the general form is acid plus base gives a salt plus water. But really, the driving force is the formation of water, right? Formation of a gas for the gas evolution reaction. And then the transfer of electrons for the oxidation reduction reactions. Oxidation reduction is long, so that's why we shorten it to redox reaction. So transfer of electrons is not obvious. You need to look at your reactant and product more carefully to find out if you have that or not. So that answers this first question. So second question. What does Li2SO4 aqueous means? Because the AQ here means aqueous. How would you name it in words? And how should you visualize what it contains, given that it looks like a clear, colorless liquid? A clear, colorless liquid like water, for example. Sometimes they have colors, but Li2SO4 would be a clear, colorless liquid. So what does it mean when you have this? So it's an ionic compound, right? Notice how you have a metal, lithium, and a polyatomic ion, SO4. So it's ionic compound, and then you have AQ. So it means that it's dissolved in water. AQ means it's soluble in water. And so the way you would call this is that it's an aqueous solution of lithium sulfate. For example, in your homework on sapling, they gave you a lot of names of aqueous solutions of salts like that. And so the way you would write the formula is that you take the name of the compound and then you write AQ to say that it's dissolved in water. So what you need to realize is that when this lithium sulfate is dissolved in water, it means it's not lithium sulfate, the compound per se, it's now ions. The ions are separated. The positive ions are separated from the negative ions. So it contains SO4 negative 2 ions, the sulfate ions. So we say that they are aqueous, which means they are dissolved in water. And then 2 lithium aqueous ions. You know, 2 because we have this subscript of 2 here in the formula. So that means we have 2 lithium ions per 1 sulfate ion. And so they are dissolved, and each ion is surrounded by molecules of water. So we say that they form spheres of hydration. So you can visualize each ion and then being surrounded by molecules of water all around. And so they are floating around, and so they are separated, effectively separated, those negative and positive ions. Also, LiSO4 aqueous means that the compound is soluble in water, right? That's how you will indicate that a compound is soluble. You will write AQ after its formula. And so this is how we would write the dissociation reaction, because so LiSO4 by itself is a solid, it's a crystal. It's an ionic compound, and most ionic compounds are you know, crystals. Sometimes they have a color, most of the time they are white. And so imagine just white crystals like table salt or you know, salts like that. And we call them salts. And when we put them, those solids, in water, they dissociate, right? They dissociate because the positive ion gets dissociated from the negative ions. And now you have ions in solution. It's not the compound anymore, it's free ions. So this is called the dissociation reaction because it shows how the compound, when it's put in water, it will make a mixture of ions, you know, floating around in water. And you need to be able to retrieve the proportions of how many positive ions per negative ions you have, right? You use the formula for that. And here we have one SO4, so one SO4, and then two Li plus ions. So that answers question 2. So now question 3, what is an electrolyte? What is a non-electrolyte? What is the difference between a strong electrolyte and a weak electrolyte? So first, let's answer what is an electrolyte. So an electrolyte is a substance that dissolves in water and dissociates into ions. And those ions will be able to conduct electricity. So that's why electrolyte, you can see in the root of the name, there is electro, which refers to electricity. And light, means you have these pieces that are able to carry the, conduct the electricity. And electricity is conducted by charged particles. So it can be ions, like here in solutions, it would be the ions who carry the electricity. But in a piece of metal, it's the electrons that are moving around and carrying the electricity. So you need, movable charges for a substance to be able to conduct the electricity. And so when you have ions in water that are free from each other and able to move, then they will be attracted, the positive ions will be attracted to, I think, the anode. And don't quote me on this, maybe I'm wrong about which way they are attracted, but the positive ions are attracted to the negative electrode, and negative ions will be attracted to the positive electrode. Sorry. So then what is a non-electrolyte? Well, it's exactly the opposite. A non-electrolyte is a substance that, when dissolved in water, doesn't dissociate into ions. It dissolves, but you don't get ions. And so you don't have charged particles, right? And if you don't have charged particles, nothing will be attracted by the electrodes, and you cannot conduct electricity. So typically, for example, sugar, that's a molecular compound. It's a big molecule made of 6 carbons, 12 hydrogen, 6 oxygen, and it's a neutral molecule. There is no negative or positive charges on the sugar molecule. Actually, it's so let's say it's glucose. And when you dissolve it in water, it stays the same. It stays as that neutral molecule. So there is no charged particle, and it cannot conduct electricity. So salt water will conduct electricity, but sugary water will not. So what is a strong electrolyte? A strong electrolyte is when the substance completely dissociates into ions at 100%, right? Completely dissociate into ions at 100%. It does not contain neutral molecules of the substance anymore, right? It's completely becoming ions in the water. And so all these charged particles will be able to conduct electricity very well. And so that's then a strong electrolyte, because it's able to conduct electricity very strongly. And then by opposition, a weak electrolyte is when the substance only partially dissociates into ions, which means some of the molecules stay neutral when you are dissociating them in water. So some of them stay neutral, and then some of them will dissociate into ions. So you have some ions, but you have mostly neutral molecules. And the few ions that are dissolved, they will be able to conduct the electricity, but there is not enough of them. So that's why it's going to be a weak electrolyte. It will only be able to conduct electricity weakly. So not as efficient as a strong electrolyte. And that's because it has only a very small proportion of ions versus the neutral molecule. So that's the difference between weak and strong electrolytes and non-electrolytes. So question 4, decide if these ionic compounds are soluble or not. And we will start with PbBr2. So for this, you will use the solubility rules that I was showing earlier. That is in this document with the list of polyatomic ion. So the bottom table is the solubility rules, and that is for solubility in water. So the question was for PbBr2. So you want to find at least one of the ion out of the two. So here we have Pb2 plus, right, and Br minus, right, because bromine is an halogen, so it's having one negative charge. So let's see, look at the left side of the table. So notice how you have two parts in this table. You have the top part with the compound containing the following ions will be mostly soluble. And then the bottom part is for those that are mostly insoluble. And then there are exceptions, and you should always look at the exceptions. So here, out of the list of ions, hopefully you're seeing the Br minus ion. Let me show you that. The Br minus ion is here. So it's part of the mostly soluble compound, right? When you have Br minus, it will make mostly soluble compound. Now we need to look at the exceptions. So you read this, when any of these ions pair with Ag plus, Hg2 2 plus, or Pb plus, the compound is insoluble. So that means PbBr2 is insoluble, even though Br minus usually makes a soluble compound. So here you want to say that Br minus usually makes soluble compound, except, and that's part of the exceptions, except with Pb2 plus. So then PbBr2 is insoluble. And so if you write it in a chemical equation, you would write S for solid, right? PbR2, and S would be the physical state. So that's for this one. The second one is LiOH. So in LiOH, you recognize the lithium, and then OH minus is the hydroxide ion. So if we pay attention here, we have Li, where is Li? Li is here. Oops. So Li is part of the mostly soluble compound, and there is no exception. So that tells you, even though here OH minus is part of the mostly insoluble compound, when either of these ions pairs with Li plus, the compound is soluble. So that confirms this will be a soluble compound. So you will want to say here that LiOH, the lithium hydroxide ion, is soluble, because Li always makes soluble compound, no exception. So you will see how the alkali metal, they always make soluble compound. You know, sodium, so if we look at the periodic table here, lithium, sodium, potassium, rubidium, cesium, francium, they will always make soluble compound. Okay, so let's move on to CaCO3, calcium carbonate. Hopefully you recognize the calcium and then the carbonate polyatomic ion. Calcium carbonate. So calcium carbonate, you can see that there is no calcium to be found in the, in the list of ions on the left side of the table here. However, we can find the carbonate here, and it's part of the mostly insoluble compound. So let's look at the exceptions. Is calcium among them? When either of these ions pairs with, so it means carbonate or phosphate. When they pair with lithium, sodium, potassium, ammonium, this compound is soluble. There is no calcium listed there. So that means calcium is not an exception. And that means it's going to be mostly insoluble. So here, calcium carbonate is insoluble. So you would write it as CaCO3 with S for solid. The physical state would be solid in a chemical equation. Because carbonates are mostly insoluble compound and calcium is not an exception. Right, so, and calcium carbonate is a chalk, chalk that you can use to draw on the floor, for example. So even though you may think, when it rains over a drawing that has been done by chalk, it's not soluble. It's only a powder that is washed away by the rain, but it's not soluble. HgSO4. Hopefully you recognize the sulfate. Hg is the mercury. So let's look at the table and see if we can find mercury or the sulfate. So we have mercury. There is no mercury listed among the ions on the left side, right? And sulfate, we find sulfate here. Sulfate is here among the mostly soluble compound. So let's see if we have mercury among the exceptions. So this would be soluble, but let's look at exceptions. So when sulfate pairs with strontium, barium, lead, or calcium, the compound is soluble. So we can see that mercury is not part of the exception. So that means it's going to be mostly soluble, right? So HgSO4 is soluble. So in a chemical equation, you would have AQ for aqueous solution of mercury sulfate. Why? Because the sulfate makes mostly soluble compound and mercury is not an exception. Now, NH4OH. So NH4OH, even though it's only made of nonmetals, nitrogen, hydrogen, oxygen, hydrogen again, it's written specifically like this so that you recognize NH4 as the ammonium ion and then OH minus as the hydroxide ion. So this is ammonium hydroxide. So let's look at these ions, ammonium or hydroxide. Here, hopefully you can see the ammonium among the mostly soluble compound. The hydroxide is there too, but okay, let's focus on ammonium. So it makes mostly soluble compound. And let's look at the exception. There is no exception. Ammonium always makes soluble compound. So that means even though the hydroxide mostly makes insoluble compound, and let's verify that when either of these ion pairs, so either of these, the sulfide or the hydroxide, when they pair with lithium, sodium, potassium, or ammonium, the compound is soluble. So this confirms that this will be soluble with ammonium. And that's like the alkali metal that I told you earlier. Ammonium always makes soluble compound. So here in a chemical equation, you would have ammonium hydroxide as an aqueous solution because ammonium is always making a soluble compound, no exception. So some of you may be wondering, that maybe you decided some compounds were insoluble when I said it was soluble. So I want to emphasize that I will use this table that I provide in Canvas, under the chapter 7 module. It's even in the chapter 5 module, maybe. So know that I will use this table to decide if something is soluble or not. So you want to use the same table preferably. Don't use internet, because internet may have too many information that can be contradictory. Another thing is when you're doing your homework on sapling, sapling will provide a solubility table. And so the best is to use their solubility table. So this way, you will be correct in sapling. And another thing is that sometimes tables say it's slightly soluble. For example, calcium hydroxide. Well, actually here, if you look at this table, here it says when OH minus pairs with calcium, strontium, barium, the compound is slightly soluble. So you may wonder, then what do I put when I have an equation that has a compound that has a slightly soluble compound? Because it's only slightly soluble, it's not fully soluble. So you will still indicate that it's an insoluble compound. So calcium hydroxide, strontium hydroxide, barium hydroxide, even though they are slightly soluble, you will classify them as solid. It will be considered insoluble in a chemical equation because there is too few ions to consider them soluble. So you can imagine that the only the surface of your solid will slightly dissolve, but then the bulk of it will stay solid. So that's how you want to visualize things. So this would be considered insoluble. So we have reached question 5. For the following mixture of reactant, you have A, B, C, D. Write the products of the reaction and tell if it is a precipitation reaction or if no reaction happens. So you have to decide, is it a precipitation reaction or not? Once you have the balanced molecular equation, write the complete ionic equation and then the net ionic equation. So there is a lot to do in each case. So let's start with A, ammonium sulfide solution and iron 3 chloride solution are mixed. So let's find their formula. So ammonium, we said it's NH4 plus, the NH4 plus ion. The 4 is a subscript, the plus is a superscript. And then it's mixed with the sulfide. The sulfide is the S negative 2 ion. Let me show you that in the periodic table. Sulfide is, coming from sulfur, and sulfur being in group 6A will make a 2- ion, right? It's a predictable ion. So you do the crisscross trick to obtain the formula. And here we have, these are super, okay, so we have NH4, and so the 2 from the charge of the sulfide will become a subscript for NH4. So we need parentheses around NH4 because there is more than one of the polyatomic ion. Remember how we put parentheses if there is more than one, but we do not use parentheses if there is only one. Here we have 2, so we need parentheses. And then the 2 outside the parentheses indicates 2 ammonium. And then the 1 from the 1 charge of the ammonium will be a subscript for sulfide. So that means it's an implied 1 here for sulfur, and we don't write it. So that's the formula of ammonium sulfide. And that's an aqueous solution. So the physical state is AQ. Next, we add iron 3 chloride. So iron 3 here, let's write its symbol. It's Fe. And the 3 in Roman numeral tells you it's a 3 plus ion. So it's Fe 3 plus. Chloride, comes from chlorine. Chlorine is in group 7A, so it makes a -1 ion. So it's a Cl. Cl. And I noticed how many of you, or several of you, don't pay attention to the fact that the L is a lowercase l. Don't write a capital letter for the second letter of a symbol. So that's the two ions we will combine to make the iron 3 chloride solution. So again, you do the crisscross trick. And so we have the 1 from the Cl will make a subscript of 1 for iron. So this is just Fe. And then the 3 from the iron charge will become a subscript for chlorine. So it's going to be a subscript of 3 for chlorine. And that's an aqueous solution, right? It's a solution, so that means it's an aqueous solution. And you mix them together and that yields. So you need to find the product now. So because we have ions, so really, even though these are formula of compounds, we know that because they are aqueous solutions, what you have in solution is this mixture of ions, NH4 plus, S -2, Fe3 plus, Cl minus. So they can exchange partners, right? The ammonium, being positively charged, will be attracted to the chloride. So let's put the ammonium with the chlorine. It's what we call double replacement reaction, because you are exchanging partners. The ions are exchanging partners. And so now we have what kind of compound when they mix. This together, you see that one positive charge, one negative charge. So that's going to be just NH4Cl. That's going to be the compound from ammonium and chlorine. Okay, so before I can write the physical state here, I need to decide, is this soluble or not? And that's where you need to go to those tables, solubility table. And here, let's look at ammonium. So earlier we saw how ammonium, is making always soluble compound, no exception. So that's going to be AQ there for aqueous. Because whenever you decide a compound is soluble, then its physical state will be AQ for aqueous. Now let's find the other compound, the other product. And that's going to be iron, and it will mix now with the sulfide. So if you do the crisscross trick, you see that the 2 from the sulfide charge will become a subscript for iron, Fe2, and then the 3 from the iron charge will become a subscript for S. So Fe2, S3 is the formula of this. So again, we need to decide, is this soluble or not? So you need to go to your solubility tables and find either Fe3 plus or S -2. And here there is no Fe3 plus. If you look on the left side, Fe3 plus is not listed. However, we do have the sulfide, and that's a mostly insoluble, it makes mostly insoluble compound. So let's look at the exceptions. When either of these ions pairs with lithium, sodium, potassium, ammonium, when S -2 pairs with calcium, strontium, barium, no, that's for OH minus. So it looks like iron 3 plus is not listed in the exceptions. So that means this is going to be a mostly insoluble compound. So here, because it's insoluble, the physical state will be S for solid, right? It's very important to not get confused. S is not for soluble. S is for solid. And whenever you have something soluble, it's AQ for an aqueous solution. So this is what we call the skeletal equation because it's not balanced yet, right? We need to balance it now. So when you're balancing equations that have a polyatomic ion, you want to count the number of polyatomic ion without breaking it apart into nitrogen and hydrogen in this case, because you can see that you retrieve ammonium there intact. So then you want to just keep it like this and only count the ammonium ion as a whole. So how many ammonium on the left? We have 2 here in this compound. On the right, we have 1. What's next? We have S. How many S on the left? 1 S only on the left there. And on the right, oops, on the right, we have 3 S, right, in the Fe2S3. So 3 sulfur. Iron, we have 1 iron on the left in the FeCl3. And on the right, we have 2 irons in Fe2S3. And then finally, chlorine, we have 3 chlorine on the left in the FeCl3. And then on the right, how many chlorine? We have only 1 in the NH4Cl. So that's the number of atoms of each kind and of polyatomic ions. So when you have a polyatomic ion that is unbalanced, you want to start by balancing the polyatomic ion. Here we have 2 on the left, 2 ammonium on the left. So let's make it 2 on the right by multiplying by a coefficient of 2. And this coefficient of 2 will go in front of NH4Cl because that's where you have the NH4. When you do that, it changes the number of Cl. Let's see, and we have 3 Cl on the left, only 1 on the right, but now we have 2. Well, let's balance the, oh, I'm missing a letter here, sorry, S is gone. So we have the ammonium sulfide here. So we have, let's balance the sulfur here because we have 3 sulfur on the right, but only 1 on the left. So let's make it 3 on the left, 3 sulfur on the left. So that means it will change the number of ammonium. So if we have a 3 here to change the number of sulfur and balance the sulfurs, right, to get the same number of sulfurs. Now we have not anymore 2 ammoniums, but we have 2 times 3, 6 ammoniums. 6 ammoniums. Let's see how. Because we have now 6 ammoniums on the left because of the 3 times 2, 6 ammoniums on the left. And we don't want to change that because we want to balance the sulfur here and we need to have that coefficient of 3. So let's make it 6 ammonium on the right instead of just 2. So we want to make it 6. And so whatever you will put here in front of NH4Cl will be multiplied by 1. So we need a 6 there instead of a 2. So 6 ammonium then on the right. So that balances the ammonium. We have balanced the sulfur, 3 and 3. So now iron, we have 2 iron on the right and only 1 on the left. So let's make it 2 on the left. And so this coefficient will go in front of FeCl3. to make it 2 iron on the left. So that balances the iron. And now let's check chlorine. We have, it's not 3 anymore here. It's instead, what is it? 2 times 3, 6. We have 6 chlorine instead. Right, we have 6 chlorine instead. Yeah, maybe I should emphasize that these are not coefficient, but you know, it's the number of so 6, because 2 times 3 is 6 chlorine, and here we have 6 chlorine, so that's balanced. So finally, this is the balanced molecular equation, right? I can write this here. That's the balanced molecular equation, right? And so the question is asking for, do we have a precipitation reaction or not? I should have answered that earlier, but so do we have a precipitation reaction? Well, yes, because we have this solid here, right? So yes, this is a precipitation reaction because we have a solid in the product. And that's Fe2S3. So that answered that question. Yes, we have a precipitation reaction. Now we need to write the complete ionic equation. Because this, you saw that, you know, it's a mixture of ions, right? So we need to write this as a complete ionic equation. So instead of the compound formula, you want to show that you have ions because this is an aqueous solution. So whenever you have an aqueous solution, instead of showing the compound formula, in the ionic equation, you will show the ions. So all of these compounds will be changed into their ions. And so I can use what I have above here to help me. So we have, so let's see, how many ammonium? 2 times 3, 6 ammonium here. And whenever you have ions, their physical state will be aqueous, right? Because they are soluble in water and floating around in water, so they are dissolved. S, how many S we have? We have 3 S. -2, again, that's aqueous. Then we need the arrow. Oh, no, not yet. Sorry, the arrow comes after the other reactant, and that's here. So then we have FeCl3. So it's how many Fe? 2 Fe. 2 Fe, and again, it's going to be aqueous. Plus chlorine, and that's another aqueous ion. So chlorine, how many? We have 2 times 3, 6 chlorine, right? You need to keep it balanced. And I could change the color here so we see better the, so 2 times 3, that's 6 chlorine, that's 2 of the Fe, and then here 3 of the sulfide, and 6 of the ammonium. And then on the reactants, on the product side, we need to dissociate NH4Cl into their ions. And so here we have these ions. So let's see how many of each. Ammonium, we have 6. Chlorine, we have, chloride, we have 6. So 6 of each of these. 6 here and another 6 here. So that's ammonium chloride. And then whenever you have this precipitate, it cannot change, right? It's a solid. It's not ions anymore. The ions have decided to form a solid together. So this cannot be dissociated because it's a solid, right? So you can only dissociate what is aqueous, right? Even so S for solid will not be dissociated. L for liquids will stay the same. Gas will stay the same. So really, a complete ionic equation can only be written for ionic compound that are dissolved in solution. So that's the complete ionic equation, and it's balanced. If you look, you have 6 chlorine on the right, 6 on the left, 6 ammonium on both sides, and then 3 sulfur and 2 iron, and you get that in this formula. So now you want to write the net ionic equation. So let's write the net ionic equation. So to write the net ionic equation, you take your complete ionic equation and you cancel or remove what is the same on both sides of the arrow. So the arrow is here. So let's cancel or remove what's the same. And so here we see we have 6 NH4 plus. So let me rewrite everything because basically you start from the complete net ionic equation and then you remove what's the same. So here we have 6 NH4 plus on the left, 6 NH4 plus on the right. So you can remove them. We have 6 Cl minus on the left and 6 Cl minus on the right. So we remove them. And the rest is different. And it makes sense, right? So the net ionic equation comes down to showing you which ions will mingle together to make the precipitate, the solid. And here you need 2 iron 3 plus ions and 3 sulfide ions to make the Fe2S3 solid. And so you have to balance it, and this is already balanced here, right? 3 sulfur, 2 iron, 2 iron. So typically, the net ionic equation of a precipitation reaction will show that the pair of ions that will together make the solid, the precipitate. So we have the same question here and another example. So B, it's copper 2 sulfate solution mixed with the potassium hydroxide solution. So that's the 2 reactants. Let's find their formulas. Copper 2 here tells you it's Cu2+, right? The sulfate is the SO4, 2-. So the 4 here is a subscript. It means 4 oxygen per 1 sulfur. And we have 2 negative charges for this polyatomic ion. So let's find the formula that they make together. And so let me rewrite this. And so you can see that we have 2 positive charges on the copper and 2 negative charges on the sulfate. So one of each ion will make this a neutral formula. So you just remove the charges and that's the formula. So what's the physical state? It says it's an aqueous solution, so that's AQ. Now, potassium hydroxide. Potassium is K plus, alkali metal from group 1A, so always +1. The hydroxide ion, hopefully you can recognize it, but otherwise, it's here in that table or above here. The hydroxide on the left side towards the bottom here, OH minus. Okay, So it's OH minus, so one negative charge. So together you can see one positive charge, one negative charge. So they can together make the KOH simply. One of each ion will make this a neutral formula. So yields, what are the product? So again, it's a mixture of ions, right? Even though we write compounds formula here, it's aqueous solution, which means you have a mixture of ions. And so the ions are free to roam around and combined with different ions. And so that's what happens. You will have the copper mingle with the OH minus, right? Positive ion with a negative ion. And so that will make the first product formula. So we have so Cu and then OH. So the one from the one charge of the hydroxide will be a subscript of 1 for copper, so it's just copper. And then the 2 from the charge of the copper will be a subscript for the hydroxide ion. But be very careful, it's 2 for the whole hydroxide, not just H. So you need parentheses around the OH to show that it's 2 of the hydroxide ion. And then again, the phase is aqueous. Well, no. Why do I say that? It's not true. We need to find out what is the physical state of this. For this, you need to go to the solubility rules. So copper hydroxide. I don't see any copper listed on the left side here. However, I see the hydroxide. And it's mostly insoluble, it's making mostly insoluble compounds. So let's see if copper is in the exceptions. So when either sulfide and hydroxide pair with lithium, sodium, potassium, ammonium, no. Hydroxide, this is for sulfurs, so no. When the hydroxide pairs with calcium, strontium, barium, no, there is no copper there. So copper is not part of the exceptions. That tells you this is then an insoluble compound when copper combines with the hydroxide. So then here we want to say S for solid. That's going to be a solid. So let's look at the other combination of ion. We have the potassium ion combining now with the sulfate. Sulfate. So positive ion with the other negative ion. So if we rewrite these, so the 2 from the sulfate charge will become a subscript for potassium. So it's going to be a subscript here of 2 for potassium. And then the one from the potassium will be a subscript of 1 for sulfate. So that means you keep sulfate like this. You don't need parentheses when it's on one of the polyatomic ion. So that's correct like this. K2SO4. And yeah, again, I don't know yet if it's soluble or not. So let's look at the solubility rules. So we have K plus or sulfate. We have K plus here. It's mostly soluble with K plus and there is no exception. And you can even confirm with the sulfate here. It's also mostly soluble, and when sulfate combines with, well, there is no exception with the potassium, of course. So this will make a soluble compound. K plus always make soluble compounds. It's one of those alkali metals that I told you about that always make soluble compounds. So that's AQ because it's soluble, so it's an aqueous solution. So this is what we call the skeletal equation. It's not balanced. So let's balance it now. Again, when you have polyatomic ions, you want to balance the polyatomic ions as a unit. So We will balance the copper, then the sulfate. So copper, we have 1 copper on the left, and on the right we have 1 copper on the right here in the copper hydroxide. Sulfate, we have 1 sulfate on the left, and then how many sulfate on the right? We have 1 sulfate on the right as well, so 1 sulfate. K plus 1 K on the right, on the left, sorry, and 2 K on the right in the K2SO4. And finally, we have the hydroxide ion, right? 1 OH minus on the left. And on the right, we have 2 OH minus on the right in the copper hydroxide. So 2. Okay, so let's balance polyatomic ions first. The sulfate are balanced, so we won't touch them. Copper are balanced. And here we have 2 hydroxides on the left, on the right. Only 1 on the left. So let's make it 2 hydroxide on the left. And multiply by 2 here in front of KOH to have 2 hydroxides on the left, to have the same amount as on the right. So by having these 2 in front of KOH, it changes also the number of K to 2. Right, 2K now on the left. But we happen to have already 2K on the right, so that balances the potassium. And I think that's it. Let's verify. 1 copper on the left, 1 copper on the right. 1 sulfate on the left, 1 sulfate on the right. 2 potassium on the left, 2 potassium on the right. 2 hydroxide on the left, 2 hydroxide on the right. So it is balanced. So we can call this our balanced molecular equation. So now we want the complete ionic equation. But first, let's decide if we have a precipitation reaction. And yes, again, we do, because we have this solid there, right? Let's emphasize that this is solid. So yes, this is a precipitation reaction because we have a precipitate in the products, and here it is CuOH 2 times. That's our solid here. By the way, these solid in precipitation reactions are called precipitate, right? We have a solid or slash precipitate. You want to know that word, and the precipitation reaction comes from that, the fact that we call this the precipitate. So let's write the complete ionic equation now. So anything that is aqueous needs to be a mixture of ions. So we will need to change all these 3 compounds into a mixture of ions. So let me reuse what I have above here. And then we'll have these 2. So we have how many copper? 1. So again, we need to say that it's aqueous. So 1 copper, 1 sulfate. So plus, let me use that. So both are aqueous, so ions in solution. Then we have 2K plus, so 2K plus. Again, that's aqueous. And then how many OH? 2 OH minus. So 2 OH minus. And again, that's aqueous. So that completes what we have on the left side. And that's balanced according to what we have above. So yields. So this is a solid, so it will not change. The solids, means the ions now are not free from each other. They are actually bonded together into a solid. And so this in an ionic equation will stay as a solid, as a compound. However, the K2SO4 is an aqueous solution. So this will be an aqueous solution. And here we have 2K, right? K2 here means we have 2 potassium ions. And let me reuse that. So K, 2K, and then 1 SO4. So it is balanced, right? You have 2 OH here, 2 OH there, 1 copper, 1 copper, SO4, 1 SO4, 2K plus, 2K plus. So that's our complete ionic equation. So let's do now the net ionic equation. The net ionic equation really shows you what's important, what changes when you mix those two solutions together. So you start from the complete ionic equation. So I'm going to rewrite this. And then you remove what's the same on both sides. So here we have SO4 on the right. So and SO4 on the left. So let's remove those. And then we have 2K plus on the right and 2K plus on the left. And the rest is different. And it shows how copper will mingle with the hydroxide ions to make the copper hydroxide. And you need 2 hydroxide ions per copper. And so the net ionic equation really shows you that this is a precipitation reaction because you had a mixture of ions and now they are forming a solid together. And so that answers question 5b. So I want to emphasize that those ions that we remove from both sides of the equation because they are the same, we call them spectator ions. Spectator means they are just there and observing and they don't contribute to any change in the equation. So that's why we remove them. And so we call them spectator ions. And here the potassium and the sulfate were the spectator ions.